All right. This is the simulation. If you didn't do this in the lab, you can go and look at it. Might be useful for you if you're not in the lab. You can simulate charges and the electric fields those charges have. Field lines emanate outward for a positive charge and inward for a negative charge. And, this comes about from the idea that we find the direction of the electric field by asking ourselves, what is the force that a positive particle feels? So if I imagine that I have a positive particle right here, it feels a force in that direction, and the electric field then is also in that direction. Similarly, over here, and over here, and over here, all the way around. I can draw as many as electric field lines as I like. I could draw an infinite number of electric field lines if I wanted, and they will always come out of a positive charge. Also notice here the electric field is bigger, closer to the charge, right? E is kq over r squared. So if r is small, E is big. So it's big here. The lines are really close together. Out here, the electric field is smaller. The lines are farther apart. For negative charges, our electric field is like this. This looks like the gravitational field of the Earth, right? Because you have attractive forces. It's identical in form, at least, not in magnitude. Identical in the way we draw it to the gravitational field of the Earth, which we saw in Chapter 0. So imagine here at point A, the field lines are more dense than at point B. They have a higher line density or a higher density. They're more dense. Therefore, the electric field at point A is bigger than at point B. So, if I were to put a positive test charge here and a positive test charge here, the positive test charge would feel a bigger force at point A than at point B. Because remember, our electric field is defined based on our force. That if I have an electric field is just force per unit charge, right? Listen, this test, or actually this test, we're just going to have forces and fields. The next step's less essential. But we have forces, and then fields are a force per unit charge. We'll see the next step later when we get into potential, but we don't need to worry about that now. All right, some more rules. The lines for groups of charges must begin on a positive charge. I'll draw pictures for these, so if the words don't make sense to you, the pictures will. The lines for groups of charges begin on a positive charge. Or plus Q, if you want to abbreviate it. Begin on a positive charge and end on a negative charge. If there's an excess of charge, the line will end at infinity. You might not know what that means. I'm going to hold you in suspense, and I'll draw you a picture in just a moment. It'll make sense to you then. The number of lines is proportional to the magnitude of that charge. Probably on the test, I'm going to give you a group of charges and tell you to draw the electric field lines. It's not going to be a complicated group of charges, but I'll give you a group of charges. You have to draw the electric field lines correctly. So the number of lines is proportional to the magnitude of the charge. Again, I'll draw a picture. And then the third part, field lines never cross. It's sort of like in Ghostbusters. Don't cross the stream. Do they say that in the new Ghostbusters? Have y'all seen the new Ghostbusters? Seriously, nobody's seen it. You've seen it? Do they say that? Don't cross the stream? That was like a classic scene, I think. Next to I've been fine. Alright, so anyway, don't cross the stream, or excuse me, field lines never cross. Because if they cross, then that would imply that the electric field is two values in the same position. That just doesn't make any sense. That's crazy. So field lines never cross. All right, let me draw some pictures. These are probably more illustrative. So if we have a dipole like this, two charges, equal value but also opposite signs, I'm going to have lines that start at the positive charge and end at the negative charge. I can draw them as many as I want. And I also want you to recognize that if I put a positive test charge, say, right here, it feels two forces. Due to this charge, it feels a force in that direction. Due to this charge down here, it feels a force in that direction. And so the net force is in that direction. And notice that the net force is in the same direction as the electric field. The electric field, in fact, gives the direction of the force, right? Electric field and force, they're linked. They're related to one another. All right, so rule number one, begin on a positive, end on a negative. Also rule number one, if I have a group of charges where I have an excess of either positive or negative, then I'm going to have lines that will go over to one side like this. And then I'm going to have also lines that go out and end at infinity. All right, so the plus 3q charge here has 3 times the number of field lines as the minus q charge. Why does it have 3 times? Why would this charge have 3 times the amount of field lines as this charge? Gosh, where does that 3 come from? Did I just pull that out of the air? Now why does it have 3 times the number of field lines? Right, I have 3 times the charge. It's directly proportional to the amount of charge. So I have 3 times the charge here, 3 times the field lines. I have 6 here, 2 field lines here. All right, and these field lines, since I have this excess of charge, they just sort of go off into space. If there are no other charges, they'll just continue on for infinity. Although the electric field will get so small that it just, these lines will diverge as they go through space. Or they'll go find some other charge to attach themselves to. All right, if I have charges that are like this, remember field lines come out of positive charges, but I don't have any negative charges here. They're going to look like this. I'll have field lines that will go apart from one another. If I draw these properly, I would have look like that, where I have this one has 3 times the number of field lines as that one. All right, that's probably not an exact representation of the fields. You can go on that PhET simulation if you're curious about what the field lines look like. Because if you imagine if I put a charge up here, it's actually going to feel a force due to these 2 charges. That'll be sort of up, and it'd be sort of up and in that direction. So there are field lines in the middle, but none of the field lines are actually going to converge onto a charge. They'll just sort of go off into infinity. All right, let's look at this. If the charge on the left, that's this one, has a magnitude of 6 microcoulombs, what's the magnitude and the sign of the right charge? Feel free to ask your neighbors what they think. We have honed in on an answer, though. We have an answer for every option amongst you. What brings that? All right, I want to stop at 1 minute, okay? 1 minute. Okay, B is right. So the reason it's B, first of all, is this charge positive or negative? It's positive because the lines are coming out. Does it have a greater or lesser magnitude of charge? It has a greater charge because it has more field lines. I have 12 field lines over here, but I only have 6 field lines over here. So the ratio of the field lines is 12 to 6. I have twice as many field lines here as I do here. So that means I have twice as much charge on that rightmost charge. If this one is -6, it doesn't tell you that it's negative, but I know it's negative because the field lines are coming in. Then this must be +12. And I know that just from looking at the field lines and counting the field lines and looking at the direction of the field lines. So as I said, on the test, 5 points, you know, probably. It'll take you 2 minutes to give you a configuration of charges. Nothing funky like we did in lab, but you know, a group of charges like this where I have a 3Q and a -4Q or something along those lines, and you have to draw the field lines for that configuration. Not guaranteeing that question, but probably you'll have that. All right, I think that's the end for this chapter. Yeah. Listen, I would look through the homework, work through the homework. You're going to see some 2D vectors. Make sure that you're up on 2D vectors. That comes up with gravity, electric forces, and with electric fields. It could be any one of those three. Make sure you understand electric fields and how those forces are applied. Be able to do simple kinematics, nothing more complicated than just sort of one-step kinematics questions, because I'm more concerned about you being able to figure out the force and then finding the acceleration and then maybe find the position of the velocity, okay? Look at the homework. The kinematics portion will be a small part of it if you have a question like that. This one, I've given this problem on test before. You can see it. I would look at the test, look at the homework. It's always a good idea to look at the homework because you know what? When I make out the test, I sort of have the topics all laid out before me. I'll go through the notes and I'll say, oh gosh, this was a good idea. Let's do this. Sometimes I'll look at the old test and say, well, that's a good question. How can I change it up? And then I'll also go into the homework and say, oh, yeah, this is a good homework question. I really want the students to know how to do this. So look through that homework. It's always a good practice to do so. Even if you don't see the exact questions, you'll see ones that are similar. Field lines, as I said, you'll probably have to draw a configuration of charges. These are your derivations, which you'll have as take-home. I'll send that out later. And then we're to chapter 1.5, or I call it 0.5. All right? How you feeling on this, okay? You want to be preparing this week, okay? Don't put it off till Saturday and Sunday night. Many of you have things going on those nights anyway. So be preparing this week, especially if you haven't been already. Ideally, if you've been preparing all along and you've been mastering these topics as we've gone along. But if you haven't mastered them yet, there's still time for you to catch up, okay? You look really excited about the exam on Monday. Gosh, you just both, all of you, have very bright eyes and you look like you're pumped. Like you could take it right now and you'd be super excited about it. All right. Let's look at chapter 1.5. It's on Gauss's law. We've covered Gauss's law already. Remember we had that whole, the flux is equal to the G, mass inside, that whole business. We can also express Gauss's law in terms of the electric field, just like we did for the gravitational field. It's identical, basically. We think of Gaussian surfaces. Let's just redefine a Gaussian surface. It is an imaginary, three-dimensional surface or shape that encloses a distribution of charge. The shape mimics the shape of the charge distribution. This is not new, right? We saw this before. Like, for example, we had the spherical mass. That's a sphere, not a smiley face. And so we created a Gaussian surface that was spherical. And then we asked ourselves, what is the flux through that Gaussian surface? And that was the field per area, or it was the field times the area. All right, so it's identical to what we've done before. The only difference that we'll have with Gauss's law here is that instead of dealing with G, we'll be dealing with E. Instead of dealing with the gravitational field, we'll be dealing with the electric field. But otherwise, this chapter is identical to the first chapter, that 0th chapter. Flux, we can imagine flux as the rate of flow through an area. All right, so let's say that we have this Gaussian surface. I'm going to imagine a Gaussian surface. It's like a sheet of paper, right? It's just a square in space. And I imagine airflow going through this. So I have this airflow that's going through this Gaussian surface. Maybe some of y'all can draw that better than I can. But I have this flow. I'm going to think of it as airflow because, I don't know, it just sort of helps me to think about it. So I have this airflow that's going through my Gaussian surface. In this case, all of the air goes through the area. Now let's imagine, my air here is going from your right to your left like this. What if I take this and I shift it like this? How much of the air now is going through my Gaussian surface? None of it, right? Because it's running parallel, it's just zooming right past that surface. So I can have it like this, and I can have all of the air go through my Gaussian surface, or I can have it like this, and I can have none of the air go through the Gaussian surface. All right? So if the surface is parallel to the flow, none of it goes through the area. So, flux then, so you can also imagine then, if we have those two extremes, as we're talking about flux, we mentioned this last chapter, chapter 0. 0 flux, maximum flux. In between, as it shifts through the angles, then I get, when I'm thinking about flux, I get some fraction of that flux. And that's why we had a trig function that came into play. Do y'all remember what trig function it was? Was it tangent, cosine, or sine? Y'all remember? It's the cosine because it's related to which of the products, the dot product or the cross product. Which dot product did we have a cosine attached to? Did I just say the answer? Yeah. What was the answer? Dot product, right? So the dot product, I remember work is f dot b, work is ft cosine theta, because we want the two things that are in the same direction. But when we're talking about area, I know it seems like these are perpendicular to one another, but when we talk about area, we assign a perpendicular unit vector to it. Remember, I think we called it n last time in chapter 0. So our flux then is the product. It's the dot product, in fact. That's also called a scalar product, if you remember from last semester, because the product of it is a scalar quantity. V cosine theta times A. All right, and this gives the component perpendicular to the surface. I'm sorry. Let me rephrase that. So this gives the component parallel to the flow. All right. Can I go down from here? Or actually, no, I'm going to say right here. So now we also express the area. This is good review, by the way, for the exam, because this stuff is going to be on, even if we don't do chapter 1.5, this will definitely be on there. So now we can express the area as a vector. Our area, A, is equal to the magnitude of the area times, let me not use that because that's what we use for cross products, multiplied by n hat, where n hat is a unit vector perpendicular to the surface. All right, so this is like chemistry. This is my surface, my vector in hat. Remember, we use those hats to denote vectors, usually for unit vectors. So it's just a vector that has a magnitude of 1. It only shows direction. My vector in hat comes out in a direction perpendicular to the surface, which is parallel to the flow. Or we're going to use it for fields. All right, so we express that area as a vector. And so now we can define our flux. Our flux is equal to the vector v, our velocity has a certain direction and magnitude, dotted with the vector a. And the vector a is the magnitude of the area that's perpendicular to the surface. Okay? So that's a general definition of flux. And you use flux for a lot of different things, especially when you're working with fields. And we've used it with gravitational fields. Now we'll use it with electric fields. In exactly the same way. Exactly the same way. All right. May I go down? Oh, actually, I don't think that we finished the clicker questions. Am I right? The clicker questions for chapter 2. Can somebody check and see where we left off on that? Clicker questions, chapter 2. Did we start them at all? On chapter 2? So we didn't do this at all. All right. We do this one? Oh, we're not on chapter 2. We're on chapter 1. Why is he going to chapter 2? All right, we've done chapter 2 in the other class. This class runs quite a bit behind the other class because we have sort of more material that we're covering along the way. We don't cover the same breadth of material that they cover. All right, so let's 1.6. We'll wrap this up. Yeah, Sadie? I don't know, Sadie. What do you mean? Okay. Go ahead and use your clicker and send me the identification number on the back. Your answers are recorded. They're just not assigned to your name. But send me the ID number on your back of your clicker. Send me the Can you trust me? Awesome. Okay. So let's wrap these up. So we did do this one? Oh, we didn't do it. Okay, well, somebody gets a freebie. Oh, shoot. Not saying B is the right answer. It's just one person said it was right. All right, so which arrows best represent the direction, the net force on charge due to the other two charges? All right, we'll stop at 33. Just guess if you're not sure. Wow. Let's see. What do you call, have I told y'all this one? What do you call Santa's helpers? Subordinate clauses. Did I tell you I wanted to be an English major when I was in college? We could all be sitting around in a circle discussing civil disobedience by Thoreau or something. Bring your Thoreau next week. We'll sit down and discuss it. That doesn't sound better. Well, I appreciate that, Brennan, but I'm not sure if some of the English professors would make good physics professors. So, what you gonna do? All right, you're sitting a certain distance from a point charge, and you measure an electric field of E naught. If the charge is doubled and your distance is also doubled from the charge, what's the electric field strength? As you're preparing for the multiple choice part, I would go through these concept tests. I'll make sure that they're up on the website. These files will be on the website. And also just go through your notes, the basic ideas that we go over the definitions. All right, I'll stop at 1 minute, a few more seconds. Let's see, so what you want to do on this is you say E equals KQ over R squared, and our charge is doubled, but then our distance is also doubled. So I get a 2 over a 4 in my right-hand side, so that means I have half the electric field, so D is right. I understand you put C because you think, oh, I get 2 here and 2 here, but recognize that one of these is an inverse square relationship, the R, and so it has a bigger impact on the electric field than the Q changes in Q does. Between the red and the blue charge, which of them experiences the greater electric field due to the green charge? This one or this one experiences a greater electric field due to this +1 green charge? Or is it the same for both? All right, I'll stop at 53. 53. Just guess if you're not sure. I think that's everybody. All right, C is the right answer. Now, you need 2 charges for a force, okay? Because you got the K, QQ over R. You got to have 2 charges for a force. But for a field, you only need 1 charge. So there is an electric field at this point due to the green charge. And that electric field is at that point whether this charge is here or not. Similarly, there's an electric field at this point. Whether this charge is here or not, that same electric field is there. So there is an electric field here due to the green charge. It's unaffected, or it's not dependent upon the blue or the red charge. Now, it's a little more complicated than that, but asking about the electric field due to the green charge, it is what it is, all right, at that point. And so it's going to be C. They both experience the same electric field. Which one feels the larger force due to the green charge? All right, let's stop at 25. 25. Okay, good. So now you sort of go with your intuition. This one, remember K, Q, Q over R, this one has a bigger charges involved, and so it's going to feel the bigger force. Which of the green charges will feel the bigger force, or will they feel the same force? Will the one on the left, this green charge, the first one, or the second one, or do they feel the same, the green charges? What do you think? The first one, right. They're third law. So the one on the left, the first one, they both feel bigger forces because there's more charges involved. You can also think of it in terms of electric field. The electric field at this point is bigger than the electric field at this point, and so the force is also bigger. Here I have a 4 coulomb charge. It sits inside of an electric field, and it feels 12 newtons of force. What if you changed it to a 6 coulomb charge? All right, doing well on this. I'm going to stop at 1 minute, 1 minute. Okay, doing sort of okay. All right, so E is right. You can go about this in 2 different ways. You can say a 4 coulomb charge and a 6 coulomb charge. A 6 coulomb charge is 3 halves the size of the 4 coulomb charge. 3 halves times 12 is equal to 18. That's probably not the way you went about it. You could also say, well, if I have a 4 coulomb charge and 12 newtons, that means my electric field must be 3 newtons per coulomb, because 3 times 4 is 12. So I have 3 newtons per coulomb in my electric field, so that means I'm going to have 3 times 6, or 18 newtons, for my new force, this charge, the force on this new charge. Bigger charge feels a bigger force due to an electric field. What are the signs of the charges on the electric fields that are shown? All right, we'll stop at 23. 23. Okay, awesome. B is right. Just look at the direction of the arrows, right? They come out of the positive and go into the negative. What do you call cheese that doesn't belong to you? Nacho cheese. Y'all have heard that one before, haven't you? Have you? But not from me? I don't think you've heard it from me. All right. Which of the charges has the greater magnitude? I'm going to stop at 22. Okay, awesome. Number of lines is bigger on the red charge, so it has a bigger magnitude of charge. What do you call a boomerang that doesn't work? A stick. I think that was the last one. Oh, and the ratio of the red to green? Anybody want to venture a guess? 2 to 1, right. So if this charge is 5, negative 5, this one is plus 10. All right, let's do one more. So just want to get the feel for y'all. I think I know what the answer is, but we're going to continue on with this chapter 1.5. But I want to know, do you want it on the exam? A, yes, B, no. Or a portion of it on the exam. We're not going to get very far into it, but A, yes, or B, no. There will be a couple of different little things that'll pop up that are slightly different from what we saw in the very first chapter. So do you want chapter 1.5, a part of it anyway, on the exam? I don't really care. Want it? We would still see that chapter on the second exam. No, it'd be the same that's in the chapter, but not. So y'all are split. I'm just going to decide, okay? Like y'all split evenly. Okay. Yeah, we're not going to have that chapter on the test. Okay. You want your vote heard, right? Yeah. So yeah, we're not going to have the chapter 1.5. We will just not have it. But right now I am going to go a little bit further because it is still relevant. Like it's a lot the same as what we saw in the very first chapter. And so it's useful just to jog your memory a little bit about flux and fields and how this whole business works. But we're going to see it in a little bit more detail. So as you're going through chapter for the exam, just sort of focus on chapter 0. All right, so if we're looking at the flux of an E field, our flux is equal to the sum of the electric field dotted with the area. Listen, we said the exact same thing before. We said that the flux was the gravitational field dotted with the area. We said I think we might have even put a summation or I put an integral sign or something. But we said the exact same thing before. And so now, since gravitational fields and electric fields, they're so darn similar because of their spherical symmetry, we're going to treat it in the same way. So we can also, just take this summation. Integral is really just a sum. That's all it is. You're just adding things up. We're going to integrate E dot dA. When you get to Calc 3, you'll add this little symbol, I think, on your integrals. You might have done this in Calc 2. Is that right? Like a surface integral? No. We're not going to actually do surface integrals. We'll do them very simply, that just sort of do them without actually using calculus. But this means that you're integrating over a surface. You might get that to Calc 3, I don't know. But you'll integrate over a surface. So we have our Gaussian surface. We want to know what is E dot dA over that entire surface. So we'll integrate over that surface. And you'll figure out the techniques of that when you get into Calculus 3 or wherever you do that. We're going to do it very simply. Let's imagine that we have an electric field. Our electric field runs from right to left, like this. I'm not going to draw the field lines in the middle, but they can be there. So I have this electric field. And then I draw a Gaussian surface. I want to make my Gaussian surface into a cylinder. So this is my Gaussian surface. Remember, the Gaussian surface is just something you make up in your mind. And you base it on, the type of configuration of charges or mass that you have, like we did in Chapter 0. But in this case, we're just sort of thinking about how do the fields and the area vectors interact with one another. And then we're going to integrate over this surface. We're going to look at the integral of E dot dA for each part of this surface. Now this surface has 3 parts. It has the end on the left, it has the end on the right, and then it has sort of the barrel shape in the middle, the round shape in the middle. It has 3 parts, and we want to look at each of those. Now, the electric field is always in this direction. There's my electric field. There's my electric field. My electric field is there. My area vectors, however, are different. See, I'll do them in pink. Here, my area vector is in that direction. Here, my area vector is in that direction. And here, my area vector is in that direction. The area vector, the n-hat vector that we're using to define the direction of our area, is always perpendicular and outward. Jesse?
The Gaussian surface is always solid.
They're hollow. So typically we'll use them, they'll have something inside of them. They'll have a mass, or they'll have a charge. All right? In this case, but for the exam, they'll have mass inside of them. So now we want to take the dot product of these vectors. The dot product of this vector is what? Think about it for a second. Remember dot products, that's E dot A. It's a cosine theta term. This is a 90-degree angle. So the dot product of these two vectors is 0. 0. Cosine of 90 is 0. Right? Anytime I have two vectors that are perpendicular, their dot product is 0. The work, if we go back to our work, work was F dot D. If our force and our displacement were perpendicular, it had 0 work being done. So our dot product here of E dot dA is equal to 0. And in fact, all around the outer surface, the integral of E dot dA, these are vectors, that it's going to equal to 0. If I think about this surface right here, the integral of E dot dA is going to be positive E times the A of that face, that particular face, which in this case would be pi r squared because it's a circle. What about over here? What is the integral of E dot dA going to be here? Not 0. Appreciate that, but...
Negative.
Okay, yeah, it's going to have a negative. It'll be just like what we had over here, but it's going to be negative. Let's think back to work last semester. If I had a force in this direction, but a displacement in that direction, what type of work was that? Plus, minus, or 0 work? Negative work, right? Remember we talked about how friction does negative work, that it takes away energy, because friction opposes the direction of motion. So, on this side over here, the integral of E dot dA is going to equal to negative EA, where this is A of the face. And so now if we want to do this total integral, which is really, we're doing an integral, but we're doing it very simply because we set up our surface to be very simple and the electric field is regular, it's going to equal to negative EA of the face plus 0 plus EA of the face. And this is going to equal to 0. Remember Gauss's law for mass? We said that the flux was like negative, I forget, 4 pi g or something, times the mass inside. We're going to see Gauss's law for electric fields as well. And in order for the flux to be non-zero, there has to be a charge inside of that object. Is there a charge inside of this Gaussian surface? No, there's a charge over here that's causing this electric field, but inside this surface, there's no charge. That's why the sum of E dot dA, the flux, the total flux that's going through the surface is 0. There's some flux going into the surface, and there's some flux going out of the surface, but those two are equal. All right, let's see what's next here. That's pretty similar to what we've seen already. And next time, we're going to look at it, or next Monday, or Wednesday rather, we're going to look at some different types of surfaces, and we'll start to deviate from that chapter 0.5 a little bit, but not that much. It's going to be very similar. We'll probably finish that chapter in a day or a day and a half, and then we'll move on. We'll probably just have one question or so on exam 2 that's from that chapter. Alrighty? So listen, in the next day and a half or so, go over some old tests, look at your homework, figure out where you're the weakest, and then come on Friday morning, and we'll spend that time going over the exam, and I'll go over sort of a summarize of what we've been doing, and then I'll answer your questions for the exam. All right, y'all have a great day, okay?